post it later. So here's our weekly schedule this week, and we have our test next Friday. And so and there's also 2 wellness days coming up. I don't know if you're aware of that. There was an email sent out recently. So be aware that those 2 things are just coming up and changing what we're doing a little bit, which is fine. So it just means that, we do have homework this Wednesday, like always. There are 2 homework assignments. And then, we're going to have a test next Wednesday, and be aware that Wednesday, so we don't have class this Wednesday. You can see it in the schedule. And then Monday as well. Next Monday is Patriots Day. So, over the next 2 weeks, we only have 4 classes. And so we're going to have this homework due on Wednesday, even though we don't have classes. I'm flexible though, so if that's a problem for you, let me know. Just in terms of being prepared for the test next week, that would be good. And then, what we're going to do today and Friday is going to be on the test next Friday. And so I'm trying to think about when to make that homework due. And so that's what the next thing that's under homework sort of talks about. I've currently scheduled it to be due after the test. So that would be, let me just write that date down. It would be the 28th. But I want to do like at least a simple kind of problem from that material on the test. And so what I'm writing right there is, yeah, you don't have to do all the homework, but I'm going to test you on that stuff. So it'd be good to like do a few of them, right? Do some of the easy ones, get a basic idea. And then the idea would be on the final, you can dig into that material a little bit more. That's what I'm trying to say there. I would also like to look at quiz 9, which I returned the solutions to yesterday, or Friday, actually. I got to that right away on Friday. Let me know if you want to look at specific things about that, but I will put that up in just a second. And be aware, we will have another quiz just like we always do on Friday. And in case you haven't figured it out yet, I always try to test on the stuff that's due in the homework that week. So in the homework this week, it's definite and indefinite integrals. That's what the test or the quiz will be on Friday. Let me pull up the quiz that we had last week and just run through it. I already had it open. I at least wanted to show this first one. That was definitely the one that people had the most problems with. So the general idea here is it's a completely made up situation that I made up, right? But if we're building a house, the idea is it's sort of usually hypothetically extends outwards and upwards when you're building it. Now, maybe practically that's not really what happens. Maybe you build the base first and then you go up, but that's the situation. We have a box that's getting bigger side to side and top to bottom every day. And we're saying it has a square base, which is why we have B's on both the bottom there, right? Because it's square, and then some height. So base and height. And so we want to maximize, this is not a maximization thing. This is a related rates thing. The question is, what is the rate of change of the volume, right? And so that's what made me realize, hey, we want d over dt of v, or dv dt, because that's how the volume's changing. And the other part of it is, okay, b and h are both functions of time. And so when you differentiate them, you're going to end up with this product rule, right? That was like when I was grading this, like first and foremost was, did you get the right answer, of course? But if you didn't, it was backtracking and thinking, okay, did they see this as a product rule? And the idea there is both those b and the h have a t inside of them, right? And so when you differentiate with respect to t, they both are derivatives. And so that product rule resulted in the next line here, right? F prime g plus fg prime. And not a ton of people, I would say, got that right? Here's my f prime, here's my g, here's my f, and then here's my g prime. And I think one of the things I want to point out here is that when you do, and I'm going to write it below the box, when you do d over dt of h, for example, that's just dh dt. Or a lot of people mess that up with the v part. When you do d over dt of v, it's not a chain rule. It's just dv dt, or v prime if you want. So keep that in mind too, right? When there's not like a chain rule involved and you're differentiating something that's implicitly has that variable, it just becomes the derivative, right? dv dt, dh dt, whatever it is. Okay. Let me just pause there and see if there are questions about this particular one or what I'm trying to say. Just remind myself of something quick too while you look at that. Anything about this one I can clarify? Not. Almost everyone got the second one right, which was wonderful to see. I did want to just point out the last one. And again, all these solutions are part of the thing I returned to you. So you have access to this, but I just wanted to point out the second one, right? So that it starts out as being a 0 times infinity situation. And you need to rewrite it so that it's either 0 over 0, infinity over infinity. And if you do the 0 over 0 form, it doesn't actually work out. So if you do 1 over x squared, for example, which a few people did, you don't actually get to a valid solution because the x isn't going to go away, quote unquote, when you take derivatives. The way that this one works, and this is a homework problem, by the way, this is right out of the homework. I can't remember if I did it in class or not, or we went over it. But anyway, I was hoping that people kind of see like, hey, do you have your homework with you? Anyway, when you rewrite it, e to the minus x as 1 over e to the x, so this thing I'm circling in blue that's now circled in yellow, then it becomes an infinity over infinity situation, and then we can apply L'Hopital's rule. And that ends up working because the x squared eventually goes away, right? Or the x goes away. And they're just eventually left with the 2, right? The bottom's not going to go away. Like the e to the x, right? When you take derivatives of e to the x, sometimes it's a chain rule, but the e to the x part doesn't change. And so that part's not going to go away. So the top part, the x on the top, needs to go away, quote unquote. And we see that here by having the x squared there. The other thing I was going to note was when you rewrite this as e to the minus x, it also becomes, I'm sorry, when you rewrite 1 over e to the minus x, you can just bring the exponent into the numerator and just make it e to the x. And when I first went through grading this, I wasn't thinking clearly about that, and I may have marked off a half point for people who didn't do that, and then I realized afterwards that it was true, so I went back and regraded. So I sent you an email about that this morning anyway, just trying to explain what I meant by that, and you can double check to make sure that yours is correct, and I didn't take points off unnecessarily is what I'm trying to say there. And so the idea is once you keep taking derivatives, you end up with this situation, right? 2 over e to the x, and when you plug infinity into e to the x, it becomes infinity, and 2 over infinity is 0. Okay, and plugging in is, of course, relative when we're talking about infinity. Anyway, can I clarify anything about that quiz? Just want to make sure you feel good about that before moving on here. Or any questions about the homework or anything before we look at the notes? Homework from this week, last week, anything that you want to look at. My time is yours. I would love to help you with that stuff. Okay. Feel free to pop by office hours, of course, as well. Yeah, great. All right, I'm going to keep looking at some notes here. So we're starting to get into some kind of tough stuff here, right? So we finished off with this idea last time about solving for the plus c, right? And keep in mind, there's some of this stuff in the homework for this week, actually. Solving for the plus c are part of some of those homework problems. And I'll still hold office hours Wednesday afternoon, by the way, if people want to come by after they've started looking at this stuff. And I just want to just mention that because I was answering a couple emails about it and it seemed like people are confused. Anyway, we're starting to get into this methods of integration, which is one of the I don't want to say it's the hardest thing in the class or anything, but it's definitely a trickier concept. And the idea is we're thinking about doing these antiderivatives, right, that I'm now boxing in blue there, where we have the little f and we make it into the big F. And we've also talked about doing it with bounds. That's how we get area under the curve, right? So that's sort of the places we've been. And we're now starting to get into, like it says here, more complicated functions. And so this is the progression. When we were doing derivatives, we moved from simple rules to like chain rule, product rule, quotient rule, right? And so now we're trying to think about undoing those rules in some sense. And so you can see we're going to look at the substitution method. That's this topic. That's going to be in this class and over the next couple classes potentially. And this is the last thing that'll be on the next test. And then integration by parts, that's the next topic. And you can see here right away under the substitution method, this is the chain rule, right? I just box it in. And just to do a quick reminder of what that would look like, it's like if we were going to differentiate x squared plus 6x plus 1 or something cubed, right? You have that function inside of something being cubed. That makes it a chain rule. And I think, I don't know, I think at this point, let me just move this over to, I can have a little more room. I'm pretty sure at this point, people feel comfortable with me just kind of writing this answer down. Right, so that's the f prime g part. And then you multiply by g prime. And so looking at the thing on the left here, this is my f prime of g of x situation, right? And this would be the g prime, right? And remember, I'm just trying to remind you of this because we're going to integrate that now, right? If you look below in the notes here, we're about to integrate this thing that I'm just trying to remind you of. And so it's helpful to remind ourselves, if we're trying to undo this, it's helpful to remind us, how do we get there in the first place, right? That's what antiderivatives are doing, as you know. They're undoing the derivatives. So we're trying to undo that. We're trying to think about, how do we get there? And so I guess the thing I'm trying to point out here too is when I kind of zoom in and I look at this thing we just wrote down, and let me get this out of the way. I can identify the aftermath of it as a chain rule because I'm kind of looking at this thing and I'm saying, okay, here's a part of the function that has something inside of it, right? And the thing inside there, if I took the derivative, it's something else in there, right? If I do d over dx of that thing, it's something else that's in the problem. And so without knowing this first part, so let's pretend I'm going to cross this part out, right? We don't know what we took the derivative of. If we were just looking at the derivative, we could still identify it as having been a chain rule because I'm seeing something that when I take the derivative, it's also in the problem. That's what I'm trying to say here. And so that kind of intuition is important because that's exactly how we're about to approach these problems, right? And that's exactly what it says right here, right? So there's a bunch of steps here, but the steps say, let U be G, and G is the thing that is inside something else. And when you take the derivative, it's also in the problem, right? So we already have this intuition from the chain rule from the derivative section, and now we're just trying to undo it in the integral, but we're using the same kind of intuition is sort of what I'm trying to say here. So let me erase some of these highlight things and add some actual words. Sometimes it's hard to convey what I'm trying to say on the iPad here. So I'll try to highlight it, but it's good to add a couple words here. So we'll go through these steps in detail as I do an example, but I think the first step is important. We're going to let U be G of X, and G of X is going to be the inside function. And the other note we should be aware of, G prime, when you take the derivative of that inside thing, that needs to also be part of the integral. right? That's how we identify these as being substitution problems. Right, I'm just trying to do that same intuition that, like, how do we identify something as a product rule, right? When we were thinking about that, how do we identify it as a chain rule? We're trying to identify these as substitution rules. And what I'm saying is you need to have a composition thing, right? Something inside something else. And that inside thing, the derivative, is also part of the function. So I'm going to, as I said, I'm going to go through these steps one by one, but I'm going to go through them as part of this first example. Okay, so I'm going to kind of keep flipping back and forth between those things. And so, look, this is kind of a tricky looking integral, right? There's a bunch of things being multiplied in there. We don't know how to do that yet. And so that's sort of the first step is, hey, does this look like any of the rules we have? And I would say, no, it definitely doesn't. So it doesn't follow any of the rules. So I would say it doesn't fit existing rules that we have. I'll say existing antiderivative rules. But notice the following. Notice that something is inside something else, right? So notice 1 plus x cubed is quote unquote inside an x to the fourth, right? When hopefully that makes sense just from the chain rule kind of stuff. And if we took the derivative of that thing, 1 plus x cubed, we would get 2x squared, right? And I also see an x squared in the integral. Right, so kind of thinking back to the thing we just said a second ago, this fits the bill, right? It's got a composition, and the thing that's on the inside, the derivative of that thing, is also part of this problem. And so this is just screaming at me, this is a substitution method. Or I should say, use substitution method. So that's kind of the first step in these problems, right? Is how do I identify which method to even use? And if you have a whole bunch of problems just sitting on a page in front of you, it's helpful to know which one to jump into, right? So this is how we identify it as substitution. In other words, a chain rule gave us this thing. So let's figure out how to undo that chain rule. Is that first sort of intuition part? See what I'm saying there? We haven't really gotten into how this works, but you see what I'm saying about composition and derivatives. I'm going to try to take this real slow. I was just looking ahead at these notes. If we could get through this page and some of the next page, that would be great today. So just a couple problems that we very slowly go through, but people are asking questions about things that don't make sense. That's what my ultimate goal is. If we go through it really slow and you don't ask questions, it would just be a waste of time. So it'd be great if along the way, you just let me know if there are things you want to hear more about. Okay. Seems okay so far? I think I can get those questions up there. The steps. Okay, great. So step 1 says we should let u be the inside thing that the derivative is also part of the function. So that's, we haven't actually done step 1. So let's do step 1. So step 1, let u equal 1 plus x cubed. Right, because it fits the description. It's on the inside, and the derivative, which has an x squared, is also part of the function. Step 2 says take the derivative of that thing. Right, so take the derivative, and then step 3 says rewrite it as du equals g prime dx. So let's do steps 2 and 3. So we're going to do du dx. So we take the derivative of u with respect to x is 3x squared. So that's step 2. Step 3 says solve for du in terms of dx. So that just means do this. Just multiply the dx over to the other side. Just going to pause right there. I've done a couple steps. see how that looks. I'm going to slide this over too. It's okay so far? We've done half of step 3. And so I just want to pause and see if a lot of this is notation. I know the notation, if you haven't been following along, can be pretty tough, right? Remember what du dx means? It means take the derivative of u with respect to x. And then I just multiplied the dx over to the other side, right? It's like I just took this thing, you move it over, and it becomes the dx over on the other side. It's okay? The thing I want to hone in on is the second part of question 3, or step 3 that I'm now highlighting. Right? It says carry any constants that don't exist in the integral along with du. And so I'm looking at this problem, and I'm going to highlight some things, so it'd be good to look at this because I'm going to erase it afterwards. I'm looking at the problem, and I see that x squared is part of the problem, but not 3. Right? So x squared I'm going to leave on the right, but since 3 is not part of the problem, I'm going to move it over to the other side. Maybe I'll leave that highlight. That's okay. Sometimes it gets kind of busy, but that looks okay. And so in other words, when you divide by 3, 1/3 du equals x squared dx. And that is something that's going to be important. And maybe you'll see why in a second. I'm not going to explain too many details before we finish this one, and you can let me know what that looks like. So let's do step 4. Step 4 says substitute in u and du. And here's what I mean by that. So I'm going to rewrite my original problem. And the idea is, based on the work we just did, I can take 1 plus x cubed, and I can replace it with u. And then I can take x squared dx, and I can replace it with 1/3 du. Right, those things go into those two locations. And then the integral, which is really complicated right now. That's something I haven't really fully appreciated. This is a complicated integral. We don't know how to do it yet. But after we make that substitution, look what it becomes. It becomes something that's not so bad. It becomes integral of u to the 4th times 1/3 du. And the 1/3 part is just a constant, and so that can just come out front and be this. And that is a super easy integral. All right, so I'm just going to pause there and let you think through that real quick, those substitutions. But the whole goal is we started with something really complicated, but we identified it as a chain rule thing. And so we're trying to like figure out the parts of the chain rule and make a substitution, right? It's called the substitution method, to make it easier to work with. And that's the thing that's super important, right? This thing we started with is really hard. This thing that we transformed it into is really easy. And so that's the whole point there. And we haven't finished it yet, but appreciate that just happened, right? We started something hard, but we transformed it in something easy that we can do. I'm going to finish it in a second, but thoughts about it so far? I'm going to wait like a full probably minute just to let people think about that substitution part.
So I see how you substituted it, but why, looking at like the original 1 plus x third raised to the 4th times x squared?
But why what? I'm sorry?
But why, like, did we have to do this looking at 1 plus x third to the 4th times x squared? Like,
Yeah, so the original problem, if we kind of Let me bust out the antiderivative rules. Where do they go? Oh, they're part of the notes. I forgot. That's not what I want. I want the notes. If we just kind of page up to the antiderivative rules, this doesn't fit into any of these contexts. So maybe you're kind of thinking, oh, it kind of looks like this rule. We don't just have x's by themselves, because one of them is like a polynomial raised to a power, and that thing is multiplying another polynomial, right? So none of these rules fit into the problem that we have. It's more complicated than that. One thing we could do, it's a mess, right? So one thing, like if we have, the problem currently says, even this alone is too much. It doesn't fit into any of these things. You could multiply 1 plus x cubed out 4 times, right? That's what it means to be raised to the 4th power. But that would also be a nightmare. It would eventually be a polynomial that you could use the anti-power rule on, but that would be, I mean, just doing that alone might take longer than the substitution rule, plus maybe you make a mistake along the way, et cetera, et cetera. See what I'm saying about that? So this could be transformed into an anti-power rule, but in its current form, it's too complicated. Other questions like that? Clarificational things? I'm going to get back to that. Maybe erase this. Oh, we're in the notes, right? Also going to get rid of that orange stuff. I just unerased all that stuff, I think. Okay, I'm going to finish this one. Are there other thoughts before we do that? So we just integrate u to the 4th, right? U to the 4th is an anti-power rule. That just becomes u to the 5th over 5, right? And so we ignore the 1/3. We do u to the 5th over 5 plus c, right? Super easy, quote unquote, anti-power rule. Right, and then we just substitute u back in. So we kind of like remove the hard part, do the easy integration, and then we put the hard part back in. Very similar to the chain rule, right? And so that would look like this. So first of all, 5 times 3 multiply together to give you 15, right? And then you plug u in. Maybe, yeah, well, I'll do it in 2 steps just in case people are confused about that algebra. So first I'll plug u in. And so from here to here, you just plug u back in. And then what I was saying was the 5 and the 3 in those fractions multiply to give you a 15 in the bottom. So that would just be like a last simplification. Not even really needed. If this is the test, this would be a great answer. But if we want to be complete with our algebra, we could multiply the 5 and the 3. And the thing I would point out is you can always check your work. And it's a good exercise for that matter, checking your work on this. Right. And I'll say it like, oh, isn't it obvious? But it's not obvious, and it would take some work to check it out. But notice, and go ahead, and I would encourage you to check this. If you took the derivative of the thing we just found, you would get back to the original. Right, the c goes away because it's a constant. Bring down the 5 and subtract 1 off the power. That'll give you the first term. And then the 5 and the 15 cancel into a 3, but then when you multiply by the derivative of the inside, it cancels that too. I know I'm kind of just spitballing it there, but just pointing out, hey, you can double check your work here and be sure that you got the right answer. And that is definitely something you should be able to do. Right, take the derivative of that thing I just wrote there. It's a chain rule, of course. Okay. Really just going to pause again here and see what's what. Anything? If you're a little intimidated, it'd be good to ask a question. Don't feel intimidated. There's definitely one of those things that can feel like, whoa, but then like once you see a couple, you can work it out. But take some effort, and sometimes you got to ask some questions. Anything so far?
That orange line or the orange circle that you drew from x squared, where it says du equals 3x squared, and you
Yep.
connected it to the other side, x squared.
Yep.
Didn't we get this 3x squared from taking the derivative of the inside of the first function, like the 1
Yes.
plus x cubed?
Yep.
So are you saying that this x squared is not correlated in any way to the other x squared?
No, what I was saying was when we looked at the original part, and the reason we made this move in the first place is when you, let me get another color going. When you take the derivative of this thing, you get part of that. That's what I was trying to show here, right? You take this derivative and you get part of the stuff that's in there, x squared. But what I was trying to point out is 3 is not over in here anywhere. That's why I wrote no. Maybe I should write 3, right? There's no 3 in there. And so that's what made me move the 3 over to the other side, because there's no 3 in the problem. And what we're going to see in the next one is the opposite of that. So let me maybe clarify this. I'm going to in red write something in here. If there is a 3 right here, then you'd have a 3x squared in there, and then we wouldn't divide the 3 over. I don't know if you see what I'm saying there. I think the next one will kind of illustrate this idea. But does that clarify a little bit what I was trying to point out with the orange that you're asking about?
Kinda, not really, honestly.
Okay, let me do this next one and let me know if this clarifies what it at all.
All right, thank you.
I think you'll see. I hope you'll see something about this one. So, and I would ask everyone before we get started on this one, what's the inside thing in this next piece, right? That's usually what we're trying to think about with substitution. We're trying to think about what is inside something else. Ideas about that? What's inside? Yeah, so someone was a little coming through choppy to me, but I also see it in the chat here that 12 minus 5y is definitely inside something, but it's not x squared. If it was inside x squared, it'd be in the numerator, right? So what's it inside?
That's the negative
5
square.
squared.
Yeah, 1 over x squared. Just a small thing. Obviously, if you realize it's inside something, but just to be clear, it's inside a 1 over x squared, which is going to help us with our derivative. And the other thing that you should notice is that when we take the derivative of that, we get the number 5. And so to the point that was just asked a second ago, that's a constant, but 5 is also in this problem, right? 5 is right here. And so 5 is part of the solution as well. So 5 is also in the problem is what I'm trying to write here. And so it starts to reveal itself. The process reveals itself once we start letting u equal blah, 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 and do all those steps. But that's just the starting intuition that's jumping us into, okay, this is a substitution rule. And I don't think I actually clarified the rest of the rules, but we did these rules, right? We got it into a very simplified thing. You integrate it, and then you just plug the u back in. I'm sorry I didn't point those out as we were doing it, but that's what we did in the last problem. And we're going to do those same steps, right? So the first step is u should be the inside thing. And so let's do that on this one. All right, so let u be what's on the inside, which is 12 minus 5y. And then we take the derivative. Now we're doing y's in this one. Don't let that trip you up. Sometimes people get a little flustered by a different variable. No problem there. Shouldn't be a problem, right? When we take the derivative, du dy, we get minus 5, right? Constant goes away. And the minus 5y just becomes minus 5. Right. Step 3 says solve du for the thing on the other side. So we're now at this step right here. We're about to do this thing. Let me do a different color though. So this is the thing that was just being asked about a second ago. And the question is, do we stop at this point, or are we going to go and do the next point? This is the thing. One of the things we're trying to convey in this example. And so get du by itself would become du equals minus 5 dy. Now in the last problem, this is where we divided the 1/5 to the other side. We did this kind of thing in the last one. And what I'm going to try to convince you in this one is this is not what we do here. And the reason is because the thing I'm about to circle, minus 5 dy, is part of the problem. Right, I've got the minus 5 dy circled in the original problem and in the thing we're going to substitute. And so that's why we can leave it and not have to divide the 5 over, because we're going to substitute out minus 5 dy directly out of that problem just with du. Let me make that note right below that. We can replace minus 5 dy with du in the original problem. Right? And we knew that was our u because that's the inside piece. All right, let me pause there. I feel like I've written a little bit, kind of try to explain some stuff. Let me slide up so you can compare it to the last one a little bit. All right, and so we're going to keep with this. I'm not going to divide the 1/5 over to the other side. That's what we're going to work with. Let me know if it's not clear why. Or maybe it'll be more clear in a second, I'm hoping. Let me see if there's anything you want to talk about right now. So let me do the substitution. Maybe that would be helpful to see. Sometimes the algebra is really holds people back on this stuff, which is too bad because everyone can do algebra. I know you can. So the original problem looked like this. And one thing I'm trying to point out is the minus 5 in the numerator, you can kind of rewrite the problem and think about it like this. Right, the 5 is just like multiplying a fraction and it goes into the numerator is one way to think about it. It's like a minus 5 over 1. And when you think about it like that, that's what lets you see, oh, okay, well, then I'm just going to take minus 5 dy and replace it with du. How am I going to represent this? How did I do it? I did it with the red thing in the last one. Right, so this thing is going to replace this entire piece, right? And then the u part is going to replace the inside piece. And when you do that, it looks like this. So let's make sure that this looks good to you. So then it would be integral 1 over u squared du. How easy is that?
So when you say plug the du equals -5 dy over here, so would this -5 dy just turn into a du? We wouldn't have to
Exactly
write
right.
anything no more?
That's right. Yep.
You wrote
I mean,
that
that's what
down.
it, when you write, it took me a long time to sort of realize these things like practically. When you write something down that says du equals -5 dy, you're saying those two things are equivalent. Like the word equivalent literally has the word equal in there, right? And so you're saying it doesn't matter whether I write down -5 dy or I write down du, it's the same thing. And so, yes, just like you said, you take out the -5 dy, you're replacing it du with du, and we've just shown, or at least based on the way we've constructed it, they're the same thing. Yes. Right, kind of an analogy of that would be like, well, 8/4 is 2. And so in a problem, you could write 2x, or you could write 8/4x. And it doesn't matter because it's the same thing, because 8/4 is 2. Right? That's sort of the same like reasoning there. Other thoughts, other sort of clarificational things? Those are great sort of clarificational thoughts that help us understand what's going on here. We're not, we haven't, yeah.
Sorry, you might have said it already, but if you're saying that du and dy are the same thing, why do you want to replace it?
So I'm not saying du and dy are the same thing. The way that we've constructed this problem, du and -5 dy are the same thing. And we replace one with the other because it helps us go from this nasty integral that we don't have a specific rule to help us with, and it transforms it into this easy integral that we can do. That's why we make these substitutions.
Okay.
Philadelphia.
I'm sorry, did you say something, Joe?
No, sorry about that.
Anyone else? Good thoughts, keep those coming. Again, we need to finish this, right? But this is the hard part. This is certainly the hard part. And just, gosh, look at how scratchy it looked with all my highlighting and stuff. Imagine not being here and just looking at this page and trying to figure out what's going on. Hopefully people watch the video. Anyway, I forget what I was just rambling about. Oh, I was just saying this is the hard part. Yeah, sorry, go ahead.
We're gonna solve this, the s(1/u²) du?
We are, but this is
solve
not
this, and then once we solve it, because it's simpler to solve now, we're gonna plug back in our original numbers.
correct. Yep.
All right, that's fine.
But the one thing that I just want to clarify, it's fine to call it S. I refer to it because it definitely looks like an S, but I'd like to start moving into the word. It's called the integrand or integral or something like that. It just helps to realize that that's not an S, and that's like a math thing telling you to do something. Anyway, let's finish it. I'm sorry?
You said it was called what? Integral?
So, integral. It's this particular one would be an indefinite integral.
Okay.
Yep. Yeah, so let's do that. So we've seen problems like that, right? You just think about that as u to the -2. Super easy. Add 1 to the power and divide by it. So this is the anti-power rule. So we'll have this. And then you just plug the u back in, just like you said. But maybe I'll rewrite it like this first, right? It looks like this. And then just plug the u back in. Oops, except I don't know what u is. It's 12 minus 5y. What do you think? And if you took the derivative of this, you'd get back to the original, right? That's always worth mentioning. Is this shouldn't be a total like I have no idea if this is right situation. It should be at least Oh yeah, if I take the derivative of that, I get the original, right? So I would like to just mention that. If I take the derivative of the thing we just found, it would be a chain rule, and we would get back to the original. And again, that might be a good just exercise to practice for the test. What do you think? I know stuff like this, if anyone's feeling overwhelmed, can feel overwhelming and like, wow, I'm never going to get this. I was already having a hard time, blah, blah, blah. But at least just notice like how interesting or useful potentially that could be. You have a really complicated function you want to integrate. Maybe it's something useful. Maybe it's going to tell you whether or not you have enough money to retire. I don't know, whatever. And you can use substitution to get there. I think I'm just going to look at just one more, and I'm going to ask you to kind of think through the steps. I just don't want to jam this all down your throat on one day. But this last one I feel like is quote unquote, I'm going to skip over this middle one because this middle one is one of the more complicated ones, I would say. I'm going to skip over this one, and that would be a good one to maybe lead with on Friday. But this one is quote unquote easy, I would say, because, well, let's dig into it. Maybe you can see why it's easy. So again, I'm not going to sort of turn you loose and let you think about it yourself, but it'd be great if as step by step, if I say, hey, think about this, if you actually do that, and it'd be great if someone would maybe type in the chat or unmute and let me know. So here's this problem. It's two things being multiplied, and one of them is e raised to the sine, right? So it's a very, anyone recognizing what u should be, right? What is inside something else? And when you take the derivative, it's also inside something in the function. And it looks like my internet's unstable. Was I just chopping?
Can you repeat that again? Because you kind of cut out for a couple seconds.
Yeah, thank you. I saw that too. So what I was just saying is it'd be great if people kind of, I'm going to do the step-by-step if you kind of think through each step, and then we'll check in with each other. So I was just curious if anyone could look at this and what do we want to let u be? Should be inside something else in the function. And when you take the derivative, we get something else in the integral. Ideas? So I'm here in sine of x. How do people feel about u being sine? Does anyone have a different thought? Does that look okay? I think that's good, right? And so that's good specifically because sine is quote unquote inside e to the x. And when you differentiate sine, you get cosine. And that's also in the function. Okay, I don't mean to write so many words all the time, but it's good to have this intuition written down. Or at least I like to have it up there, so if you don't write it down, you can come access it later. Okay. So you with me on that? You should be sine. All right, let's do it then. So u is sine. Differentiate it. Du is cosine. And then solve for du. Sorry, I'd actually wanted to let you think about those steps, and I just kind of rushed through it. Just get so excited sometimes about this stuff. That's really the truth. But that is one of the things we want. We want to use this thing, and we want to use this thing, and then we want to make the substitution. And so let me just see if there are questions about the work first. But if not, it'd be great if you would make the substitution. Right, so this is your chance to rewrite the integral, kind of dig your hands in and see if this stuff makes sense. So take our original integral and rewrite it with the substitutions. All right, just take 1 second and See if that looks all right. And so one of the things that's just kind of occurring to me that maybe is tripping people up is things aren't in the right order the way they had been before. So maybe it would help you to, you can change the order of multiplication, right? And these things are just being multiplied. And so I don't know, maybe it helps to look at it like this if this is confusing you a little bit. Because then it at least groups the things together that you're trying to substitute. How's that look? So after you've thought through that substitution, right, U goes into the sine spot. These two things get replaced with cosine dx, right? And it just looks like integral of e to the u du. How's that look? Which is, right, that's the easiest integral there is, of course. All right, that looks okay. Then we just integrate it and it stays exactly the same. All right, it's the best one out there. And just plug the u back in. That's it. This is actually one we probably didn't even need the substitution for, right? I mean, we could pretty easily notice that, hey, when you differentiate e to the sine, you get what we have. I don't know, maybe some people kind of notice that to begin with, but oftentimes it's too complicated to kind of just do that right off the bat. All right, well, that's all I've got for today. Like I said, we'll finish that last one. We'll start off with that on Friday. We don't have class Wednesday, that's why I keep referring to Friday. But I will be around on Wednesday for questions. We still got some homework due on Wednesday. Let me know what I can do to help you. I'll stick around right now too if anyone has any questions. Thanks, guys.
Thank you. Have a good day.
Thank you.
Thank you.
Thank you.
Can I ask you to explain something to me real quick?
Yep.
Get du equals cosine of x dx.
Yes.
Or from there.
I'm sorry, explain it from there. Is that what you said?
Yeah, from there. Yeah.
So I just rewrote the original problem, right? And then I'm trying to, and I just moved this around to kind of group the things that we're going to substitute. I saw that these are the two things that were actually grouped together over here, right? Cosine dx. And so I just wanted to put them next to each other just in case people didn't see that, so that they could see this substitution a little bit easier. So that was just from that step to that step. And then you're just making substitution, right? So u was sine. And so I just took out sine and made it a u. See that?
Yep.
And then the other part, cosine dx, is just du. And so that's what happened on that piece.
Oh, okay. And then you take the antiderivative of that.
Yeah, which just stays the same, right? So that's why, so, you know, from here to here, the integral just went away and you have a plus c.
All right.
And then you just plug u back in.
That sounds good. Thank you.
Sure.